Okay, so here's where we were last time. We were talking about scalar surface integrals. We had just gotten through talking about scalar line integrals. Let me remind you of what makes these interesting. Scalar line integrals were interesting because they were just qualitatively different as a target of the chop it up, add it up strategy. It was just doesn't really fit any of the previous molds. It's not a single variable integral. It's not a double integral. It's not a triple integral. It's a different thing. So we had to write down a different Riemann sum in recognition of that, different notation for the integral, different tools for how to compute it. Right? Those details are all different, but it remains, and this is very important, that it's still a chop it up, add it up kind of a deal. So same with scalar surface integrals. I mean, so you look at this picture here, this is what our domain looks like. Maybe I want to compute the mass of this thing. Maybe there's a bunch of grass growing on this hillside with, grass density varying as a function of altitude, or something like that. And, how many total blades of grass? Well, it's a problem, right? Even computing the area of this hillside is a problem, yeah.
Just to check, did you start the recording?
Oh, thank you for asking, and I am only 80% sure I did. Now I'm 100%. Yeah, yeah. Thank you for asking. It's I cannot be trusted on that. Okay, so we have another qualitatively different kind of a situation, right? So we can write down a new Riemann sum, and here it is. That says we're going to chop this domain up into little pieces, and on each piece, whatever it is that we're computing, and as you all recall, I like the mass application because it's so relatable, right? Intuitively relatable. On each piece, the amount of mass is, density times area. This density being interpreted as mass per unit area, right? So mass per unit area times area gives you mass. Add up all the little pieces of mass to get the total mass. Well, our estimate of the total mass. And then, of course, we have to take a limit as we slice finer and finer to make sure that our round-off errors go away. And again, hopeful that the function is sufficiently regular that the round-off errors actually do. And for the purposes of Math 212, they always do. Okay. So, new kind of Riemann sum, and as a result, new kind of notation. We talked about this last time. I think it's very plausible notation. Okay. So, for example, this was the example we just got through talking about, basically. If you want to compute the mass of a curved sheet of metal with non-constant density given by some expression, well, total mass is the sum of a bunch of little pieces of mass. Right? So, mass is an accumulating quantity, accumulating in this new sense. And on each little piece that we slice up our surface into, mass is density times area. Right. Okay. All right. So that's about where we left off last time, as I recall. So how do we compute these things? It's nice to have a notation and a strategy, but we do not want to be stuck actually directly manipulating Riemann sums and trying to compute directly from the Riemann sum. We all have flashback memories from Calc 1 classes where we had to do Riemann sums of single variable integrals, and it's so much harder. So how can we get our hands on computing this? We're going to take the same approach that we took to scalar line integrals. We're going to recognize that there's something about these domains that we don't like. I don't like the fact that this domain is dimensionally awkward. I can deal with the curves and bumps, I guess, but this whole two-dimensional thing in a three-dimensional space, that's the killer. That's why it cannot use triple integral techniques on that. It's not a three-dimensional thing. I can't use double integral techniques because it's in R3, right? It's just, we don't have any techniques for this. So, I'm going to view it as being an image of a domain that I do like. There's a two-dimensional domain in a two-dimensional space. That's a good old, plain old, regular old, familiar double integral domain right there. So if I can view this as being an image, then I can talk about taking the integral on my undesirable domain and pulling it back to an integral on the new yellow, much more desirable domain. So it's our usual pullback strategy. As usual, we need to figure out what the stretching factor is. So when I chop up my new domain over here, I'm going to have little pieces of little pieces of area in my new domain. My parameterization, we talked about last time. This is just a parameterization of the surface. My parameterization is going to take that little yellow rectangle of a size that I can write down, du, dv, and it's going to do stuff to it. And what's going to turn out is going to be a very different shape. This is now a little two-dimensional thing in space, for one thing, which has been stretched out by this parameterization. It's not necessarily a rectangle anymore. And remember, we talked about this with change of variables, that locally, what happens to little displacements? How does that arrow? What happens to that arrow when we push it through the parameterization? Well, there's a linear transformation that applies to it. So we made the case with change of variables that when we apply a linear transformation to a rectangle, which is made up of two parallel lines as part of it, for example, we know that linear transformations take parallel lines to parallel lines. Right? And then there's these parallel lines here. Linear transformation takes those parallel lines and turns it into these parallel lines, approximately. So the linear transformation that sort of addresses the first order behavior of this function, how does this function change, sort of nearby, is going to take a rectangle and have as its image something that looks a lot like a parallelogram. Right? So same case that we made in talking about very analogous situation for change of variables. It's just that now this parallelogram is, hovering in space instead of being in R2. Okay, so how do we compute the area of this parallelogram? Well, you have to recall, way back when we talked about how to compute those areas, and I'm going to need to know these two edge vectors. We have a chapter 1 formula. If you give me two edge vectors of a parallelogram, in space, if I know those two edge vectors, then there's a formula for computing the area. Old chapter 1 fact. How am I going to get those vectors? Well, those are the images of these vectors. So I need to understand these green vectors. I need to do whatever I got to do to turn them into these purple vectors. Once I know the purple vectors, I can use chapter 1 formulas to compute the area that I'm actually interested in. And keep in mind, that's our goal right now, is for the moment, is to figure out, what is this area ds. Okay. All right, well, so we've been here before. We know how to turn input vectors into output vectors. The derivative transformation does that for us. We applied that with change of variables. We applied it with scalar line integrals. Same idea. And here's what it looks like. These two input vectors, that one there is in the E1 direction. It has length du because this rectangle has width du. So it's E1 du. Right? Chapter 1 observation. And so what do I get for this output vector then? I just apply the derivative transformation to E1 du. And you can see that in wherever I wrote, there it is. We take this input vector E1 du, that's this input vector here. I'll just look at one at a time. That input, oh, wait a second, down here, here we go, E1 du. Right, we're going to apply the derivative transformation. Missed. The derivative transformation turns that into this output purple vector. And computing, you get that output vector xu du. Now this computation is a lot like a couple of calculations we've done already. Apply the derivative transformation. We have a bunch of techniques for applying derivative transformations, right? For one thing, scalars factor out. So this du here factors right outside because it's a linear transformation. Okay. Secondly, derivative transformation applied to a standard basis vector is a partial derivative. Right? From way back in section 4.5. 4.5? I guess it's 4.5. Anyway, partial derivative section. So, okay. So, input green vector, apply the derivative transformation, output purple vector, xu du. So, that's the calculation of what's going on here. Now, apply the same thing to the second input vector. This second input vector goes in the E2 direction and has length dv because this rectangle has height dv. So it's E2 dv. E2 dv is the input. Apply the derivative transformation, go through very similar arguments. The scalar dv factors out. Derivative transformation applied to a standard basis vector is a partial derivative. Same argument, right? And we get that our output vector is xv dv. So we now have formulas for these two output vectors. These two edge vectors of our parallelogram were practically there, right? We wanted to compute this area, ds. What's the area of that parallelogram? How does our initial little rectangle get stretched out? By what factor does the area increase, right? We just need to compute that ds. We have the edge vectors. Right, here's a picture of what we're talking about here. We know that vector. We know that vector. We want to compute ds. Full confession, yes, of course, the surface actually kind of curves a little bit away from this parallelogram. We're approximating, we're doing a linear approximation of the surface, so it's not going to be perfect, but in the limit, as n approaches infinity, right, we expect we expect the error to go away. So computing the parallelogram, which for approximation purposes is close enough to ds, it's just the cross product. xu du cross xv dv. Which is right here. This area that we're interested in is xu du cross xv dv. Okay, so that gets us, again, to a little bit more algebra. Now let's see how this algebra goes through. Well, here's a scalar that factors out. Here's another scalar that factors out. Scalars factor outside of products. Right? So now, in a super convenient bit of good fortune, the output area that we're interested in, not only do I have a formula for it, but I have a formula for how it relates to the input area. Du dv. I have explicitly my stretching factor. How much do I multiply by the input area du dv to get the output area, this parallelogram, this ds, little piece of the surface? I have the factor by which the parameterization stretches areas. And this is something to memorize, the magnitude of xu cross xv. Make sure to memorize that formula. Very important. So because this formula is so important, this vector that we're taking the magnitude of here is also pretty important. Xu cross xv. Turns out this vector is important for a lot of reasons. One quick observation I'll make. Xu cross xv. Look back at this picture. I've already forgotten my color choices. Let's see. Well, I didn't really make one. But xu cross xv, xu is parallel to the surface. xv is parallel to the surface. So the cross product is going to be perpendicular to the surface because it's perpendicular to both of the input vectors, both of the tangent vectors. So that's, by the way, in case you're curious, why we call this vector n, xu cross xv. This thing whose magnitude is our stretching factor, we call it n because it is a normal vector, and it turns out that it's a really important normal vector. No surprise, that you can see already, this is not just any normal vector. This is the normal vector whose magnitude is the stretching factor. Okay. Alrighty, so that allows us to write down this theorem. If you want to compute a scalar surface integral, which we do, right? We want to compute masses of things. We want to compute how much grass is on a certain hillside. this surface integral, I can do the usual pullback, right? I can take my parameterization, recognize that position as a function of u and v. I would like to just, I need to figure out how to change my differential here. What is ds? I can't just rewrite it as du dv. Of course, du dv is a totally different area. But I now know my stretching factor, right? This computation up here, right? xu cross xv is our stretching factor. Stick in your stretching factor and you're good to go. All right, so we have a plug-and-chug formula for how to compute scalar surface integrals. Everybody happy? Cool. Okay, so let's do one. We'll start with the metal sheet application. Not that it matters, by the way, right? So we've already seen that there are several different applications of scalar surface integrals. How you turn a question into a scalar surface integral is just a matter of observing that the application fits the usual requirements. It's got to be an accumulation. The domain's got to be a surface. Big deal. So the thing that makes this application interesting is here I'm going to show you how to actually compute this Riemann sum. Right? This is a strategy for representing something. This is a Riemann sum. How do you compute it? Well, you use this formula up here. Now notice that the formula, everything in the formula is based on the parameterization. You can see it right here. You're going to plug in, for x, y, z, you're going to plug in the parameterization. For the stretching factor, you're going to do a computation that is based on the parameterization. You're taking crosses of partials of the parameterization. So everything comes from the parameterization. It's just like with scalar line integrals. With scalar line integrals, everything that you do, everything involved in the pullback is the parameterization. Here, everything involved in this pullback comes from the parameterization. So step one, parameterize. Right? We've got this the surface. Let's look at our surface. We're looking at a graph of that function. There's that word, graph. Right, so make sure you're good with chapter 2. You remember exactly what, we're not looking at a level set of this function, right? So looking at the graph of this function, how can I parameterize this graph? Graph parameterization, right? It's the perfect tool for this situation. So here's our graph parameterization. Now let me just remind you, how you construct the graph parameterization. This is a chapter 2 thing. We talked about it in the section on parameterizations. I don't remember what number that is. But if you're a little sketchy on the graph parameterization and its variance, right? When we talked about polar graph parameterizations and spherical graph parameterizations, and whenever you can solve for one variable in terms of the other variables, or there's several variations of this, make sure you're good at those, because the first step in every one of these scalar surface integral questions is how do you form the parameterization. So got to make sure you're good with that chapter 2 stuff in order to be able to do this chapter 5 stuff. Okay, so there's our parameterization. Now let's think about some details here. We are looking not at the whole graph. The whole graph is an infinite paraboloid. That's not what we're interested in. We're looking at the part of this graph sitting over the unit disk in the xy plane. Well, this, keep in mind when you have a parameterization, those being x and y, this being z, the unit disk in the xy plane, well, x and y are u and v. That means that the domain here is the unit disk in the uv plane. Yeah? Everybody see how that happened? One of the nice things about the graph parameterization is that it makes the domain pretty easy to write down. Okay. All right. So there's our parameterization, and we're off to the races. It's plug and chug at this point. Right? Here's our explicit formula. Plug in the parameterization for x, y, and z. Okay, we are going to have to compute this stretching factor. So we've got a little bit of algebra we've got to do here. I'm going to have to take two partials of my parameterization. I'm going to have to take a cross product to get capital N, and then I've got to compute the magnitude of that cross product to get the actual stretching factor. So let's, take a deep breath and plow forward on that. It's just algebra, of course. XU, partial derivative. XV, partial derivative. Y'all can compute partial derivatives. You get that and that. So again, make sure that you can do that. It's a technique we talked about a lot in back in chapter 4, taking partial derivatives. Now, take a cross product. Well, it's chapter 1. Right? Make sure you're good at those. Don't forget this little minus sign. This is a dangerous little oops. It's so easy to forget that little minus sign right there in the second term of the cross product. So anyway, just a reminder. Very common mistake. And then taking the magnitude. Well, that's an very old chapter 1, second day of class deal. And here's our result. Our stretching factor is that. How are we doing? Let me take a pause here. Anybody have a question? Everybody on board? Okay. Right. Oh, yeah, please, go ahead.
I have a question.
Yep.
Can you remind me again why x sub u and x sub v are the partials of those?
Oh, that's just that's the definition. I mean, this subscript of u means take the partial derivative.
Okay.
Yeah. And so remember where that came from is I wrote down xu. Well, I wrote down xu du here because that's what we computed in this algebra right here. This was a partial derivative, right? Standard basis vector, so partial derivative. Yeah. Cool. Okay. Alrighty. Right, so here we go. So there's our stretching factor. Everything else is a matter of plugging in. So we just did the stretching factor, so let's deal with that part first. Right, there's our ds. Our ds progresses just as described. The stretching factor is what you multiply by du dv to get ds. We just computed it. Stick it in there. Cool. Everybody happy? Okay, next, how does our density function develop? Well, let's see here. We've got to go back and remember what is this density function. Here we go. The density is z squared. So you're going to write down z squared. Now, again, a very common mistake that students make is they get to the z squared and they're like, what do I do with the z squared? Do I just leave it there? No. Don't forget what the parameterization is. The parameterization is telling you x, y, and z. Right? So this thing right there is the z. So said differently, you plug in what your parameterization tells you about x, y, and z. So z squared is, let's see, u squared plus v squared, quantity squared. That's what that turns into. Yeah. And lo and behold, notice that we now have a plain old boring double integral. Right? This domain D is the unit disk in the UV plane. This is an integral, du dv. Compute by whatever techniques. Yeah.
Have you ever run across a situation where the function of the surface isn't continuously differentiable?
Where you mean where the integrand?
Yeah.
Possibly, but we don't need it to be continuously differentiable. We just need it to be continuous in order to be able to do integrals with it. So if you're wondering if you're going to ever run into a situation where you can't integrate because the integrand is not integrable, not in Math 212. I mean, they're in a more advanced math class, you might, and that's a really interesting conversation, but it's not Math 212 appropriate. So yeah, right, no problem. Anybody else? Anybody see how these plug and chug? By the way, how would we compute this integral? Anybody have any clever ideas? a lot of potential for this to get ugly, right? I mean, look, our domain is a unit disk, which is round, which has, therefore, when you slice it up, you're going to get square roots and the bounds. The integrand here is already looking pretty ugly because of square roots. Ugh. Anybody have any clever ideas of how to turn this hard problem into a much easier problem?
You can convert to cylindrical.
So I like where your head's at. It's polar coordinates, though,
sorry,
right?
yeah.
Yeah. So that's exactly the right idea. So pick a better coordinate system is the point. Now this is it's a double integral, thus polar coordinates, but exactly. Yep. So think about, and by the way, this is, kind of like with symmetry, these kinds of opportunities are not going to announce themselves, right? It's one of the unfortunate things about textbooks. Textbooks give you integrals like this, let's say in the section on polar coordinate integrals, and it's basically telling you, hey, here's a question, and by the way, here's the answer. The answer is use polar coordinates, right? And you know it because it's in the section on polar coordinates. Outside of those kinds of situations where the context just effectively gives you the strategy for the solution, you have to be on the lookout, right? So when you see stuff like this, don't just kind of get into the mode of, okay, well, let's start slicing, right? Think about your options. Hey, is rectangular coordinates a good coordinate system here? What are my alternatives? What would happen if I did this in polar coordinates? Or hey, maybe a different change of variables, right? But kind of always heads up for what your alternatives are before you just start plowing ahead with calculations. Okay. And of course, always be on the lookout for symmetry. My favorite computational method, right? This one doesn't, but sometimes. Okay, there's another example here. I'm not going to go through the details of this one, but it's a pretty entertaining example. Lots of good little twists and details to worry about. And so I'm going to encourage you all to read this one on your own. And we're going to move on to vector fields. Okay, so let me remind you where we're at in terms of our study of integrals. There was first three kinds of integrals: single variable integrals, double integrals, triple integrals. These were the big three that we started with, right? And then in the last couple of days, we talked about scalar line integrals, definitely a different kind of a Riemann sum. And now today we finished up talking about scalar surface integrals. So we're sitting on 5 different kinds of Riemann sums. Again, all of them chop it up, add it up, right? Which is an important point of view on what they really mean. But with different details because they're geometrically different contexts. Okay. All right. So I'm about to show you. We won't finish it today, but we'll definitely get to it today. Number 6, our 6th kind of integral is a new kind of a line integral. It's a line integral. It's an integral over a curve, just like the one we just got through studying. But instead of taking this curve and wanting to compute like mass, we're going to be interested in computing a different thing that I'm not going to disclose just yet. I want to leave that for when we get there. But we're going to be computing a fundamentally different quantity. That fundamentally different quantity we're going to get to it by coming up with a chop it up, add it up kind of approach, and then the details of the situation are just going to be fundamentally different, and it's going to give us a new kind of a Riemann sum. So number 6 is coming up in out of 20 minutes, 30 minutes, something like that. The thing that's going to make it fundamentally different is the integrand will be a fundamentally different thing. So before I can go down that road and tell you about this new kind of line integral, integral number 6, I have to introduce you to the fundamentally different object that will be our integrand, right? And so, in other words, I can't tell you that story until you know what the players in the story look like. So here's what those players look like. They're called vector fields. Let's say vector field. I'm just going to give you a bunch of examples. I'm just going to go straight to the pictures. Here's our first example of a vector field. A vector field is something that associates to every point in space a corresponding vector. So at that green point, for this particular vector field, at that green point, I associate that blue vector. Now, here's a different point. And notice I associate to that different point a different vector. It's not the same vector. Right? Here's yet another different point there. And at that point, I associate a fundamentally different vector. Right? So anyway, that's what a vector field is. Now, why would I be interested in such a thing? What physical phenomenon does this remind you of? And when I wrote this one down, I was thinking about gravity. Right? If you think about it, gravity is a thing that for every given point there is an associated vector, right? And that is the gravitational field at that point. Right? If I hold up this thing, right? If I hold it here, there is a vector that tells you the force of gravity that the gravitational pull of the Earth applies to this thing. If I hold it over here, it's a slightly different vector because it's in a different location, right? People in Australia, gravity pulls what we would call up, right? So different points, different vectors. Okay, so this is called a gravitational field. And it's a special case of a more general category that I like to call force fields. Not in the Star Wars sense of the word, right? But a field, a vector field, where the vectors represent forces. Okay, all righty. So there's a vector field. Here's another vector field. Now, notice it remains that at any given point there is an associated vector. Here's another point. There's a associated vector. Different points, different vectors. This one could represent forces, I suppose. It's not clear how we'd construct such a situation. Gravity doesn't do this. What I've drawn here was intended to evoke a different kind of a situation where, for very different physical reasons, you might want to, at a certain point, associate a certain vector. And this, what I was thinking of here is flow of a fluid. Right? So if you have, let's say, a river. Right? I don't know if you all are aware of this phenomenon, but near the edge, near the bank of the river, the water's not flowing very fast. But when you get out into the middle, the water's flowing a lot faster. And that's just how rivers work. So you can describe that story by the fact that, anywhere you are, you can just observe, well, the flow is what it is at that point. And you can, let's say, write down a vector that represents the velocity of the water at that point in the river. Right? So now, it's still just a vector field. It's still, for every point there's an associated vector. But I want to point out that this is representing a very different physical phenomenon. Right? The way fluids flow, that's a completely different physics thing than the way gravity applies forces. So, vector fields make sense in different contexts. They apply in different physical circumstances. Quick pause. Anybody have any questions about any of that? Everybody happy? Okay. Here's another flow field. Well, correction. Here's a vector field representing another instance when I was thinking about flows. And, what is this? Well, I guess you could think about this as being the flow of water in a pot that I've stirred. Maybe. It'd be kind of weird to think about this representing forces. Right? If this is representing forces, no matter where you are, the forces are telling you to go around. Seems like that would conjure a situation where we just get going faster and faster and faster. So not that can't happen, but anyway, it'd be a weird kind of a force, but an easy kind of a flow. Here's a vector field. Now, what does this represent? Well, gosh, I guess it could represent a force field. It'd be kind of a weird force field where the further you are from the center, the the harder you're being pulled would seem a little bit strange. Here's a situation, though, where you could think of this as being a force field. Suppose we were looking from directly above, we were looking straight down on a hill, and these arrows represent the force of, that gravity pulls you on the map, right? If you're standing at the very top of the hill, you drop a marble at the top of the hill, it just sits there. Pretty much, eventually roll off. But if you drop a marble on the side of the hill, there is instantly a very significant gravitational force due to the angle of the hill there. And, well, generically, for hills that tend to, sort of paraboloid-esque, kind of do like that, the further you are away, the stronger the force. So maybe this is representing forces in that sense. Could this represent flows? A flow of a fluid? What do you think? How would this represent the flow of a fluid? I don't want to say it can't happen, but there's an eyebrow raiser situation here, which is if this is representing the flow of a fluid, then outside of this circle here, there's just fluid just persistently, consistently flowing outward. Where is it all coming from? Right? This would be a strange flow of a fluid. Now, where is it all coming from? Could have an answer. It could be that, so this is a, water flow, and there's an underground river that's coming out of the ground right there. And so that's where it's coming from, right? Or maybe it's raining on this hill, and as the rain drops on this hill, well, the water tends to go outward, away from the hill. So there's scenarios where this could represent the flow of a fluid, but it conjures different sort of physical scenarios. Yeah? Everybody good? Okay. All right. So anyway, different kinds of vector fields communicate different ideas. Let's see. Where is the next thing? Yeah. Okay. Here we go. Here's another situation where vector fields come up, and the amusing thing about this one is it's already come up. We just didn't notice, and that is gradients. So here's my observation. If you have a function, now think back to chapter 4. If you have a function, real valued function, you can talk about the gradient. Right? And we know that, if you're looking at a real valued function on Rn, you compute the gradient at a given point, and that gradient is a vector. And we never quite took that last step because we didn't know what vector fields were at the time. But let's take that last step now. Oh, so you're telling me for every point in Rn, we're writing down an associated vector. It's a vector field. Right? The gradient is a vector field. So here's an example. And, so a la chapter 4, here's a real valued function on two variables, x and y. There's the formula for our function. And if I compute the gradient, right, total yawn, there it is. We know how to compute gradients. You take the partials, you assemble them into a vector. Right? And notice that this gives, for any value of x and y, plug in any point x and y, out comes the associated vector, that gradient. And what we were looking at a minute ago is actually a picture of this. So if you give me this point x comma y here, the associated vector, and I guess I didn't draw this to scale, the associated vector at that green point x comma y, look at the formula for the gradient, it's exactly double of the position vector. So at that green point, here's the position vector, the gradient points in that same direction, and I should have drawn it twice as long. The trouble with drawing vector fields fully to scale is you end up with a lot of ink on the page, and so sometimes people don't draw them to scale. Okay, all right. So in all of these examples, this is just for sort of definition purposes. I'm going to say a vector field is a function from Rn to Rn, and that doesn't seem right. What we said initially was for every point there's an associated vector, and well, if you look carefully at what this says, that is what this says. For any given point in Rn, there is an associated vector in Rn. We're just making we're making conflicting, that's not right. We're making different interpretations of the Rn's here. This represents a point in our Rn, This represents a vector in the same Rn. It doesn't represent a different Rn. It represents a vector in the same Rn. Okay, so like so in this picture. Now, not this picture. Here's how we would sort of naively view a function from R2 to R2. For example, as a change of variables function. Right, we would think of our input space and our output space as being separate worlds, points in, points out. Right? To understand this as a vector field, we have to view it in a totally different way. Now, still R2 to R2, but we interpret the domain R2 as giving us locations in our space, and we interpret the target R2 as giving us vectors that we associate to those locations. Everybody see what I'm talking about? It's a little bit weird, right? By the way, awkward. We have here a picture that we're using to represent a function. Let's count those. We have this one up here where you have the domain and the target drawn separately. Then we have graphs. Then we have level sets. Then we have images, so parameterizations, what's going on with parameterization. That's 4 different ways that we've had up to now to draw pictures that we associate to functions that are qualitatively different constructions. What we have here is number 5. This is yet a 5th way to draw a picture. So now again, I make a big deal out of this because it's important that you understand the difference between these different constructions. Please don't look at something like this and think, oh, graph. I see students do this all the time where they say, oh, if I want to compute what that slope is, I guess I'll take a derivative of that function. Right? This is not a graph. The derivative of this thing that is not a graph should not be expected to give you a slope, and it doesn't. So, heads up, right? Different kind of a construction, and you got to think through, how does algebra relate to geometry in this new situation? Okay. Couple of examples. Here's another example. By the way, all these examples fit into the category of suppose someone gives me an algebraically represented vector field like I have here, f of x, y is equal to 2, 1. That's algebra, right? How do I draw the picture? How do I represent this? What does this vector field look like? Right, so the several examples. There's not going to be a single, here's how it always works method. I'm just going to show you some examples of where you can kind of make sense out of it in different contexts. So this one, f of x, y is 2, 1. I claim that looks like what I've got drawn up here. This is f of x, y equals 2, 1. Notice all the vectors are the same vector. As they should be. I mean, if you think about it, that's exactly what this says. This says at every point x, y, at all of these different locations, we always write down the same vector. At this point, 2, 1. At this point, 2, 1. At that point, 2, 1. Always the same vector, 2, 1. Does everybody see how that makes sense? Everybody see how I got this picture from this formula? Okay, what about this one? F of xy equals xy. We've already written down one that's not terribly different from this. This says that whatever your point is, understand the position vector. The position vector for the point x, y is the vector x, y, and the field vector is that position vector. That's what this says. This says at any given point, the field vector is the position vector for that point. So that's something like this. Now I've drawn this in a haphazard way. I just wanted to point out for example, at this point, there's the position vector, and that is the vector that we associate to that point. And at this point, there's the position vector, and so this is the vector that we associate to that point. And artistic competence aside, that's what happened at all of these points to give all of these field vectors. Yeah? Pretty good. Okay. Okay, next one. Now this one's a little different. Again, I'm just going to show you a few examples. I can't show you all of the examples because there's just too many different kinds. But just want to kind of show you a few tools that are useful sometimes. What is this guy? F of xy is equal to negative yx. Well, notice that at that point, x comma y, if I look at the field vector negative y comma x, the dot product is 0. So they're perpendicular. All right, now you just got to look at the algebra and notice that that's how this works out. X comma y dot negative y comma x, always 0. You can also observe that these two vectors have the same length. So this is an interesting vector field. We're looking at, for any given point, we're looking at vectors that are same length but perpendicular direction to the field vector. To the position vector, excuse me. Okay, so here's an example. At that point, with that position vector, the field vector has the same length. Again, I didn't draw it to scale, and in a perpendicular direction. All right, for any given point, perpendicular direction. Oh, come on, green. How are we doing? Questions about that? Okay. Now, you might be wondering, how did I know that? So by the way, this I'm going to loosely call this a swirl, right? This is a stirred bucket of water or something like that. How did I know that it was swirling around counterclockwise? Wouldn't it have been possible that it could have been going the other way? So for that point, maybe the field line could have gone that way. Come on, green. That way. And then like this and like that. And how do I know it's not swirling clockwise? Right, what is it about this algebra that tells me that this is counterclockwise, not clockwise? And here, this is an unsophisticated resolution, but just plug in some points. Right, and then you can see with a couple of examples, what's going to happen. So let's look at this point right here. That point right there is 1 comma 0. So when x is 1 and y, when y is 0, this formula for the field f was, let's see here, negative y comma x, which I can see, if x is 1, right, then I know that's 1. And if y is 0, then I get 0 comma 1. Let's just plug it in. Anybody see what I did there? Okay, so perpendicular to the position vector, and so we've already argued that it's either clockwise or counterclockwise, and with this one example I see, well, it's clearly not clockwise, therefore it's counterclockwise. Okay, cool. Okay, so a few examples that you're going to go through in the exercises. I'm going to just hit the ground running with using vector fields now. So there, as I mentioned, the reason I'm showing you vector fields is because they are going to unavoidably, they're going to be critical participants in this next application I want to talk about, which, by the way, is an important application. We're going to compute something called work. Y'all remember way back in chapter 1, right? One of the first things we did in chapter 1 is we talked about how to compute work. Y'all remember that conversation with the dot product? And, the high school point of view on work is that it's force times distance, and then they put an asterisk and say, well, the thing is, though, you have to make sure that the force is going in the same direction as the displacement. Well, it's much simpler just to say work is equal to force dot displacement. Force is a vector. Displacement is a vector. It's just downright natural to think of that as a dot product, and we went through and checked the algebra works out. It is exactly that dot product. Okay, so we're going to address here a further complication of suppose that I don't just want to be able to account for the different directions, but suppose I'm not even going in a straight line. What if I'm not doing this? Right? What if I'm going along a curved path? Does that mess things up? How do we deal with that? And even worse, what happens if the force is not constant? So maybe the force is that at that location, but it's that at that location. I can't just say force dot displacement if the force doesn't even stay put, right? The force is changing throughout the process. Wow, okay, so this is going to be a much harder problem. So this is the problem we want to address. It's a new kind of a question. Now, you see the domain, and you're thinking line integral. Right? And we got to go through a chop it up, add it up, and make sure that this actually is, that everything fits all of the criteria that we can claim line integral. So we got to go through that process, and what we're going to find is that it does not fit. This is a different application with a fundamentally different kind of resulting Riemann sum. Okay, so anyway, here we go. Okay, so first, chop it up, add it up. I argue that the total amount of work that it takes to do that whole thing is the sum of how much work does it take to move along each little piece, right? So the sum of that amount of work plus that amount of work plus that amount of work, right? Work is an accumulating quantity. If you're talking about how much gas do you burn, how much of your battery do you discharge, in driving along a particular road. Well, just keep track of how much gas you burned on each one of these little segments. When you add them up, that will tell you the total amount of gas you burned. So, accumulating quantity, I can break this up into little pieces and then make a summation argument of some sort yet to be determined. Okay, so, on each little piece, let's look at this little piece here. Here's a little piece of curve. It's not exactly straight, right? Our total curve is quite curvy, right? But when we chop it up into little pieces, they're still not going to be perfectly straight. But I make the usual hand-waving appeal to intuition as I slice up finer and finer, as long as my curve is not severely, contorted. In the limit, most of these pieces, they're going to approach straightness. And so I can approximate this task of moving along that little piece of curve sufficiently well in the limit by moving along this displacement vector, delta x. What do you think about that? Everybody happy with that? This being, xi minus x, I guess that's the way I have it written here, xi plus 1 minus xi. Okay, so it's just a displacement vector, it's a straight line vector, and the curve hugs that vector close enough. Okay, so we're displacing by way of this vector. Now again, keep in mind we've sliced up our curve into itsy bitsy teensy weensy pieces, and so the force that I'm experiencing is approximately constant. Now, I need to put some conditions. I need my force. The formula that gives me my force, the vector field that represents my force, I need that to be continuous so that as my scale gets smaller and smaller, it gets closer and closer to being constant so that the limit, in the limit, all round off errors will go away. But anyway, as long as we say f is continuous, we're kind of returned to our familiar old Chapter 1 interpretation. We have before us the question of suppose I displace by way of a vector, and in doing so am using a certain force. How do I compute the total amount of work on that displacement? Well, it's work is equal to force dot displacement. Okay, so we have a good chop it up, add it up thing going on here. Let me summarize what we've done. Work is an accumulating quantity, right? And on each little piece, work is equal to force dot displacement. Now, let's take a pause here. what's going on with this minus sign? Where'd that come from? This is a physics thing. It's not that big a deal. Hopefully y'all have seen this before. If not, here's a very quick little physics lesson. When I hold this pen or the stylus right here, and I talk about the force, there's actually two forces. Right? So the two forces that are acting on this stylus are, for one thing, gravity is applying a force downward. Right? On the other hand, I am applying a force upward. Right? In some minuscule amount, my arm is getting tired here because I am exerting a force in the upward direction. I can feel the weight. I am pushing up. Yeah? So, when you say the force, you got to be careful. Which of these forces are we talking about? And notice that these forces are exact negatives of each other because, well, they add up to zero. The pen is not accelerating. It's sitting there, not moving at all. If the acceleration is zero, the total force is zero. That means that these two forces are exact negatives of each other. So we have to ask ourselves, which of the two forces are we actually interested in? Are we interested in the force that I'm applying up? Or are we interested in the force that gravity is pulling down? And the answer is it depends on what the question is asking. And so there is no sort of always this, never that. You have to look at the phrasing of the question, interpret appropriately. What are they asking me to compute? And what have they given me? Right? It's all about the phrasing of the question. So let's look at the relevant phrasing here. There's a force field on the domain. Okay, that doesn't really resolve it. Which is this the force that's being applied to me, or is this the force that I'm having to push to overcome it? So you can see how it's phrased here. Moving along the path through the force field requires work to oppose the given force field. So we have to oppose the given force field. What that's telling me is that the work that we're applying is the negative of the given force field. Everybody on board? Okay. So that's where this minus sign comes from. The phrasing of the question. We know we're interested in the work that we're doing. We have been given a force that's being applied to us. We are working to oppose that given force. Okay, so heads up. Again, you always have to be on the lookout for this. Okay, so so anyway, that minus sign being recognized. Work is force dot displacement. The grand total amount of work is the sum of the little pieces of work. And now I'm just going to stick that in there. Work is the summation of those little pieces of force. And here we are with an expression. All together, we have that work is computed with that expression there. And this is where we were kind of, I don't know, on some level, we were maybe preparing to spike the football here and say, hey, Riemann sum, scalar line integral, parameterize, plug and chug, declare victory. But it's not. This is how it worked out, but that simply is not a scalar line integral Riemann sum. This is weirdly different. Look at what we've got here. What we're adding up is not a density times a size. That's a vector quantity. What you might want to call the integrand here is a vector valued thing. It's a vector field. Right? This, what you might want to call the differential, is not a size. It's more than a size. This is a displacement vector. This is a position differential. Right? It's both a length and a direction. That's not magnitude of delta x. It's delta x. So this is a different deal. Oh, by the way, this is not a elementary school times type of multiplication. That's a vector dot product. Simply not what we had in the scalar line integral context. So I cannot just declare this to be a scalar line integral and go about my business. It's not. It's a brand new thing. This is integral number 6. Now, so let me remind you, single variable integrals, double integrals, triple integrals, scalar line integrals, scalar surface integrals were our relatively new ones. And now we have this, again, new and different thing. This construction, I call it a vector line integral because the integrand is a vector. The differential is a vector. As opposed to, in the previous examples we've seen, the integrand has been a scalar, the differential has been a scalar. So I think the term vector line integral makes a lot of sense. Here's the definition. Vector line integral. This Riemann sum that we just, kind of stumbled across in working on a particular application, and we represent it with this notation, which again I think is super plausible. But before I go through and talk about the notation, let me take a pause. I've said a bunch of stuff here. Is anybody uncomfortable with anything about this definition? Any questions? Feel free. Everybody see how this is an importantly different thing? It's just not. It is not exactly the expression that we wrote down with scalar line integrals. So, okay. All right. Okay, so let's talk about the notation. Dx represents this, the differential of this displacement, delta x. By the way, we've already talked about the dx vector. This is not new, right? This is we talked about the dx vector as a tool for part of what we were doing with scalar line integrals. So it's our old friend. Let's see here. Then there's this. Highlighter. There's using a single integral symbol. Well, because we're adding up over a curve. We're taking our domain, we're chopping it with one index. So a single integral symbol makes sense. As usual, put the domain, whatever your domain is, in this case a curve, put that as a subscript, the usual way, right? And the only other thing to really I guess I should mention, the integrand, of course, is the vector field that I'm looking at. Right, that's just a recopy. That doesn't really take much to motivate. The one additional thing I want to talk about is the recognition of the fact that that's a dot product there. Right? And so that shows up, you'll notice, in the notation. So you don't say, it's very important, you don't say integral f vector dx vector. It's f vector dot dx vector. Because you are dotting, in the Riemann sum, when you look at what's actually happening here, that is a dot product, not a, what else could it be? I suppose you could say, but anyway, it's a dot product. So that's got to be in the notation there. Okay, so again, for the 6th time in this course, here's a notation. Don't ever forget that when you write that down, what you're really saying is you're writing down a Riemann sum. Right? It's a shorthand for a Riemann sum, that specifically Riemann sum. Okay, so how do we compute these things? Let's talk about the very plausible scenario that I want to move along this road, having to apply forces to oppose this given vector field. How much work does it actually do? It's nice that I've got a notation for it and everything, but I need a number. How do I compute these things? Please tell me that I don't have to actually crank out Riemann sums, right, directly. That's super annoying. Okay, well, good news. We're going to attack this problem the same way we've attacked all of our other recent problems. I have a domain that I don't like. There's my curve that I'm, either driving a car, opposing the wind, or opposing gravity. This is my path over which I'm doing a vector line integral. I don't like it as a domain. I don't like it because it's dimensionally awkward. It's a one-dimensional thing in a two-dimensional context. What do I do with that, right? So I'm going to try to view that as being an image of a domain that I do like. Interval on the t-axis. Wait a minute, this sounds really familiar. Is this causing flashbacks for y'all? Right, we have a curve that we're viewing as an image. Total deja vu. It's a parameterization. This is the exact same situation that we were in when we were doing scalar line integrals. So this is a flashback of a flashback. I remember previously having done this. Right? So not only can I use parameterizations in this situation, I already have used parameterizations in this situation. I don't even really need to do that much more work. We've already written down several different things. Let me just remind you, we've talked about, let me pick a better color. We've talked about the length of that little piece of curve as being ds. And we got our hands on ds by understanding this position differential dx. And we computed that dx was x prime dt. This is all, what was that, yesterday I guess it was. Or maybe it was, I can't remember, they all blend together. Recently, for sure. So, this is not new work. This is just recall. Yeah, everybody on board so far? So now we went to a little bit of extra trouble then to compute, what is this ds? And just as a reminder, ds, we argued was magnitude of x prime dt, and then we interpreted this as our stretching factor. Right? All this is old news. All right, now does any of this help us with our current situation? Let's look back at the integral we're interested in rewriting. Where is our, here we go. I'm interested in rewriting these kinds of integrals. And here's some really good news. This is surprisingly good news. Notice conspicuously missing from this expression is ds. I don't need to know ds. It's not there. I don't need it. Right? So the fact that I have already computed a stretching factor, I don't care about any of this. I don't need the stretching factor because that was just a way to get my hands on ds, and I don't need ds. All I need is dx. Right? Dx is x prime dt. We've already, not only have we already computed it, it was our first step in more stuff that we've already done that we no longer need. Dx is x prime dt. Done. Right, again, going back here. This is the thing that I need. That dx. And I already had it. So this is one of the weird things about vector line integrals. I mean, vector line integrals are a more sophisticated construction. They address a kind of what you might call a harder kind of a problem, this vector-oriented kind of a problem where you're not just thinking about scalar quantities, you're thinking about directions and how do these directions relate to each other. It's a more sophisticated construction. And the expression for computing it is easier. It's just dx. I don't need to take the magnitude of anything. It's just a dx vector. And dot products are multiply and add. No square roots. It's kind of weird. It's a good news, though. Okay, so with that computation having been done, here's how we compute vector line integrals. How am I on time? 30. Okay, I'm good. I want to compute a vector line integral. Dx is x prime dt. Plug in your parameterization. By the way, let's recognize that x prime, of course, is derivative of the parameterization. So in the usual way, everything that we get here, we're just doing a pullback through the parameterization, and there's our handy-dandy formula for computing line integrals. And I think I have just enough time to go through one example here. Let's see, how many examples are there here? Oh, there's several. Okay, all right. Anyway, I want to do one example at least. Okay. All right, I want to compute work. I already know work is going to be a line integral, vector line integral specifically. Now let's think about the details. We are walking counterclockwise along the unit circle from 1, 0 to negative 1, 0. We're going to have to parameterize that. Let's come back to that in a moment. The wind necessitates pushing with an opposing force given by that. let's think about the minus sign. Again, you always have to worry about this. Excuse me. This f that I'm given, do I want f or do I want negative f? Okay, is this the force that I am pushing with, or is this the force that I am pushing against? Right? Is this the force pushing on me, or is this the force that I am applying in reverse? And again, it all comes down to the phrasing. This says that the wind necessitates pushing with this opposing force. So, good news. This question is telling us the opposing force that we are applying. I am pushing with this opposing force, F. I am trying to keep track of the force that I am pushing with to compute the work that I am exerting. Right? So, it's just F. There's no extra minus sign in this case because of how this question was phrased. Okay. All right, so it's as easy as integral f dx. Okay, now let's parameterize our curve. Let's see here, go where we have a little bit of room to draw a picture. Unit circle from 1, 0 to negative 1, 0 counterclockwise. All right, 1, 0, negative 1, 0 counterclockwise on the unit circle. There's our curve going that way. Easy parameterization, right? This is our usual unit circle. We're starting at 0. We're starting where theta is equal to 0. We're going counterclockwise. The radius is 1. It's the easiest parameterization of a circle, and it's that right there. Everybody happy with that? Okay. Okay. What do we do with our parameterization? Well, if we know x, it's easy to compute x prime. So there's our x prime. Notice I don't have to compute a stretching factor. It's not like there's some scalar that I'm multiplying by a size. This is the x prime. Dx is just x prime dt. No magnitude computation required. No square root required. Again, I think it's wonderfully, sort of mystifyingly convenient that in this more sophisticated calculation, right, I have less algebraic inconvenience. No square roots. Okay, so dx is x prime dt. Just plug it in. Everybody happy? Let's see here. Now the f. Okay, now don't forget our vector field. See, negative y comma x. Don't forget the parameterization is telling you x and y. Right? So negative y comma x is negative sine t comma cosine t. Right, so let's see here. So x is cosine t, and y is sine t. So negative y comma x is the vector field. Everybody see what happened there? Do be careful. It's easy to, we're taking this formula, we're plugging into that formula. It's easy to kind of get it all backwards, so take your time, slowly and carefully, and make sure you get that right. It's easy to miss a negative or get the things reversed or whatever. Okay. And now we have a single variable integral. In fact, it's a really easy single variable integral in this case because of the Pythagorean identity. And there's our work calculation. Yeah, everybody good? Okay, great stopping point. We will pick up here on, it's going to be a while. So I hope y'all got the email that I sent. Let me go ahead and stop the recording here.